The title of my talk, The Brain and Its Mind, the Need for Philosophy, I could have also said the need for interdisciplinarity. And neuroscience, if you really want to say, it's sort of a hybrid subject matter, right located between different disciplines. And what I'm focusing on is particularly the brain-mind relationship. Pascal already indicated that. You see here, Frankenstein movie, highly recommended to download that. It's very funny. And of course, I will take, the mind is a very complex, you have different kinds of mental features like sense of self, consciousness, mind wandering, and all kinds of things. I will focus here particularly on consciousness. So one of the key problems which we're really confronted with, and I think we haven't resolved that yet, that there is a contingency. There's no necessary relationship between brain and mind. These are like apple and oranges, as we say here in the Anglo-American world, two different kinds of things, and we don't really know how to link them. Yeah. And it doesn't, when we see neuronal features, neuronal activity, we see in brain imaging pattern, we see EEG pattern, we see in singular cell pattern, we see computational model link and its pattern, but we simply do not see where and how can that be related to mental features. So there is, philosophers say, there's no necessary relationship, but it's contingent. As I say, as we say in the Anglo-American world, it's like apple and oranges. So there's a gap. That gap has been thematicized in philosophy in various ways. Explanatory gap problem, heart problem, and so on and so forth. Here it's just necessary, how can we bridge that gap? And I say, maybe we need to consider also a little bit the conceptual background. Why? Because many of the concepts which we're dealing with in current neuroscience, like self, consciousness, mind wandering, and many, many others, have their origin in philosophy. They have only been investigated in neuroscience in the last 40, 50, 60 years. And before, they were a lot discussed in philosophy. And that has a long tradition. And that means there also come certain presuppositions with it. And I want to shed some light of these presuppositions and how they impact our experimental designs, and if a change and how a change in these presuppositions might change our view of the brain-mind relationship in neuroscience. And for that, I want to take you with me on a little interdisciplinary journey. So that's basically one part, and you will see this is a schema. I know this is a very complex schema, but you see that's basically sort of a methodological interdisciplinary loop I want to take you through with in this talk. So when we do neuroscience, you usually do, okay, we just do my computational modeling, I just do my empirical data, then I have a hypothesis, I have experimental variables, data, and then I obtain some facts, and then I publish a paper. However, your neuroscience and the kind of concepts you use and the way you use them strongly depends upon certain latent, usually tacit, implicit presuppositions. That's where philosophical concepts come in. We have heard all these different neurodisciplines, neurodidactic, neuroeconomy, neurosociology, and here neurophilosophy is another one. So these kind of concepts, and I'm always surprised, even when we, in our lab meeting, we discuss really hardcore, absolute details about task-related activity or resting state activity, and suddenly how is that related to certain, let's say, sense of self, what we're working a lot on, and then a lot of conceptual background comes in. I'm always amazed by that. And I give you one example, how, for instance, certain philosophical presuppositions come in and how they can restrict or widen our empirical view. So let me give you a little example. One really presupposition that here, and I specifically speak for the Western tradition, not so much for the Eastern, Far Eastern tradition, the Chinese, Japanese tradition, that we assume the mind to be very special. Obviously, philosophically, you probably know, that goes back to René Descartes in the 16th, 17th century, who said, okay, we can observe the body from the outside, we can apply science, we can apply mathematics, geometry to the body because we can observe it in third-person perspective. However, the mind, we cannot observe from the outside. There's nothing we can observe, it's all internal. And that, for that reason, he said, okay, the mind is special and the body is non-special. And of course, you say, come on, this is old, this is 3-4 centuries ago, Descartes, Cartesian dualism. However, you'll be surprised when you look a little bit into detail in current neuroscience, particularly neuroscience of consciousness, for instance, then you see this dualism is preserved. And suddenly you say, okay, we have a lot of neuronal mechanisms in the brain. These are basically the non-special neuronal mechanism, but then you have a very special mechanism, which is just specifically for consciousness. And that special mechanism is distinguished from all other neuronal mechanisms. So I tell you, and that will come more often, the typical integrating information, that's the integrated information theory. That's a special mechanism compared to all other non-special mechanisms. Global neuronal workspace theory. So you have to get access to the global neuronal workspace theory, preferably through the dorsolateral prefrontal cortex. That's the dorsolateral prefrontal cortex. That's a special mechanism compared to all other non-special mechanisms. So now the dualism between mind and body somehow has been preserved and somehow suddenly surfaces in two kinds of mechanisms. Yeah, one related to consciousness, the other one related to the rest of the brain. Yeah, and when you go into more detail, this can be more refined. You have within your certain dichotomy, then within the special mechanism, you have a division, you have a distinction, you have more reflective consciousness, phenomenal consciousness, psychology, net block, access consciousness, phenomenal consciousness. And then you have also different neuroscience theories. The ones which are more about reflective access consciousness, probably global neuronal workspace theory, particularly higher order thought theory, recurrent processing theory, and then the integrated information theory and embodied approaches claim more to be about phenomenal consciousness. And then you have sort of the non-special mechanism. Yeah, of course, that is non-consciousness here in philosophy. Psychology is unconscious processing. And when you look the Friston work, this is predictive coding and free energy, because these are a theory of the brain in general. So you sort of have still the dichotomy, the dualism between special and non-special, and this mental features like here, consciousness, are considered to be special compared to the rest. So there's a difference, yeah? And the question is, and you see that, as I said, this is a paper we published in 2020. It's an overview about different theories of consciousness. So it's really, most of them are really embedding and integrating a special neuronal mechanism for consciousness within the otherwise non-special neuronal features of the brain. So when you bring, let's say, the metaphor of the iceberg, which I like very much. So basically we say, okay, the surface, this is consciousness, is very special. That is what is very special, and we currently don't know. And then there is a lot of unconscious brain, non-conscious, pre-conscious, non-special mechanisms. So the question is, and that's another presupposition, maybe we need to consider the non-special mechanism in order to understand the special mechanism. So then suddenly the dualism between these two kinds of mechanisms evaporates. So then suddenly you look, maybe what do they share? So what do the non-special mechanism and the special mechanism share with each other? Yeah, so that's what we called in a paper in the 2020 common currency. It's a shared feature. So you see how we move the presupposition of mental features being special to the assumption, maybe if they share something, maybe they're not as special as we think. Yeah, so there's not a special add-on mechanism. Yeah, so then you say, yeah, Northoff, then what do they share? Please be a little bit more specific. This is a nice conceptual argument, but what do they share? What do these two supposedly special here, the mental level and the non-mental level, share with each other? So and that leads to the assumption that maybe here, when you go back, this is a beautiful quote by Nikola Tesla, you know, the Tesla cars by Elon Musk, and Tesla was an inventor at the end of the 19th, beginning 20th century, and highly recommend look into his Wikipedia entry. Very interesting guy, very interesting, very clever guy, very idiosyncratic. And he had this beautiful quote: if you want to find the secrets of the universe, think in terms of energy, frequency, vibration. And instead of universe, you could also say mental features. Yeah. So here he goes to very basic features of nature. Yeah, of nature, physics, biology, energy, frequency, temporal, spatial dynamics. You will hear that a lot from me. And that's basically the idea that we say, and maybe, and I will give more flesh to the bones of temporal spatial dynamic, that are shared between neuronal and mental features. So that's basically their common currency. It's like we all speak English. That's why we can understand each other, and that's why you can communicate with me. Now, let's say if I were starting speaking German, you would not understand. We would have no shared language. We could not exchange ideas, and we could not transform your questions into my answers and back and forth. Yeah, same here. Neuronal and mental features share something so they can transform into each other. Yeah, and as I said, I will bring more flesh to the bones. So that's really, you see here, you have a shift in your presupposition, yeah, from a very special mechanism, integration of information, global neuronal workspace, higher order cognitive mechanism, and so forth, here to very basic, we just look at the time and space. However, now you say, yeah, Northoff, please, then how is time and space related to the brain? And that's a key question. That's the next slide. So we often think of time that basically the brain just operates in time. Yes, certainly true. It operates in the time of the world. However, the brain has its own inner time and space. And philosophically, that is very interesting. There's a distinction that goes back to Immanuel Kant, philosopher, German philosopher, 18th century, where he distinguishes between inner time and outer time space. So the outer time is in the world, the inner time is in the mind at this time. So now when you extend Kant to the brain, you say maybe the brain has its own inner time and space. And that is not completely identical with the world's outer time and space. So now, here I give you a view of how you can view. Usually we have sort of a container view. Your brain operates in the time and space of the world. So it's just, and then we look for the neural correlates of how we perceive the outer time and space. For instance, how I move now from one time point to another and how you perceive that. Yeah, so that's basically just the brain itself has no inner time, but it's just operating in outer time. And then you have neural correlates of how you perceive and cognize this outer time. Yeah, I think we just had it before when we're talking about 15 seconds can be quite long in the time perception, how we perceive those 15 seconds. So however, here that we call this the construction view, that the brain itself constructs its own inner time. Yeah, and I will give more support and more indication what I exactly mean by inner time, how it does it. Yeah, so and then you have a matching between the brain's inner time space and the world's outer time space. I'll give you an example. I was just talking about the 15 seconds. When you are exposed to the 15 seconds, and then you have the feeling, oh, they're very, very long. So how is that possible? Then you have the feeling the 15 seconds feel like 2 minutes. Why? Because your own brain's inner time is not in complete accordance with the outer time / the 15 seconds. So you get a delay or you experience them as faster or slow. Yeah, depending upon your own brain's inner time speed. And that inner time, particularly inner time and also inner space, is central, and I will show you that in some empirical data. So, and here, for instance, you can say, I give you an indication. We have, what do I mean, for instance, by temporal dynamic? You go to the seaside, you see big waves, they're extremely slow, but very, very powerful. That is the kind of waves you want to have as a surfer. That's why you go to Hawaii or you go to Portugal and do surfing. And however, there's plenty of faster waves. They're not as powerful as surfer. They're of no use for you. And exactly the same happens in the brain. So you have a time series, let's say you analyze an EEG or MEG or intracranial recording, but even in fMRI, you get a time series. And you get, basically, you decompose the frequency spectrum, and then you have different kind of frequencies. Yeah, you have gamma frequencies, 30 to 40 hertz, alpha, you all know this, 8 to 13. And then you have also, very important in MRI, you have the infraslow frequency from 0.01 hertz to 0.1 hertz. So this is 100-second cycle duration to 10 seconds. So this is really slow stuff, but, and that's important, that slow stuff is extremely powerful. So these waves correspond to these waves. Yeah, and I will come back to that. So it just gives you an idea that here by temporal dynamic, it's a very basic phenomenon of nature. Just like Nikola Tesla said, go back to the basic units of nature. So basically we look, and then we also see, I will give you example, topography of the brain, the intrinsic spatial organization and the intrinsic dynamic, and that may be shared. And that can be studied empirically. And I will bring you examples for that. So now you say, yeah, what about my presupposition? So remember, I started with a specialness, and then I said, I contest that specialness of mental features. Then I said, maybe mental features are non-special. Yeah, they shared between neuronal and mental features and all neuronal features. So they're non-special. Yeah. So and that led me to search for certain features which are the most basic features of the brain, temporal spatial dynamics. If I had always looked for something special, I would have not come up with the temporal spatial dynamic. So meaning my conceptual shift from specialness of mind to non-specialness of mind led me to a new neuroscientific concept, the temporal spatial dynamic. Yeah, I would have not come up with that otherwise. Yeah, because time and space is the most basic features, they're not special at all. Yeah, so then I would have probably looked for some special cognitive features. And that's exactly what most of the other theories of consciousness do. They look for some special cognitive features and its neuronal correlate, or perceptual sensory feature like the posterior cortical hot zones, IIT. Yeah, so I would have looked for that. So that shifted the concept, even if you're not interested in all this philosophy and says this not of go home, that you say, no, but it is relevant because it shifted my view of my neuroscientific concept. And now I can say, okay, maybe how can I investigate all of this temporal spatial dynamic? And that lets me now to the next discipline. Yeah, that's what is, so how can I transform this philosophical presuppositions of non-specialness into probably real neuroscientific experimental measures and data. For that, I go into physics and engineering because they know what is dynamics, particular dynamics. You find a lot of in electrical engineering, signal processing, and the dynamical system theory. You find a lot of interesting stuff. Yeah, and of course, in the topography, I focus here more on the dynamics. Topography is the intrinsic spatial organization, like core-periphery hierarchy, certain gradients. I will touch upon that later. Yeah, so now you see, I started in philosophy, came to neuroscience, and now I suddenly go into physics and engineering. What on earth is Northoff doing? Because I want to have some measures. I want to have operationalization of my temporal spatial dynamics. Yeah, so I already indicated that you have a brain here. You see, for instance, also certain topographical organization. You have the time series. I already mentioned that the different frequencies. And importantly, I mentioned that the slower frequencies are much more powerful here. The slower frequency, so this is the frequency, this is the power. And here you see much more power in the slower frequencies than in the faster frequency. And you also see that there's a double lock because this kind of curve is called scale-free activity. You have a certain shape of the curve and you have long-range temporal correlations across the different frequencies. So, and if this curve is steeper, let's say like this, then of course, obviously you have more power in the slow frequencies relative to your faster frequency. So there's a certain structure in the power spectrum. And that's basically the structure, the organization of your dynamic / your power spectrum across the different frequencies. So you already see here, this is again a slightly different approach. Usually you would say, okay, it's just one frequency. Okay, you're an EEG person, you just look for alpha frequency. Or you just look for theta frequency and memory related process. But that may be just the tip of the iceberg. Underlying, you have the theta or your alpha is embedded into an overall structure of your power spectrum, yeah, related to the other frequencies. And that is what is called scale-free dynamics or scale-free activity. Yeah, and then you can have, for instance, also cross-frequency coupling. The other way, what you can do with this time series, you can also plot it in the time domain rather than going into the frequency domain, and then you can have temporal autocorrelation functions. So you investigate the correlation of your time series across time. So basically you correlate each time point with all other time points, and then you get these time lags and you get an autocorrelation curve. And that's basically the degree to which your signal correlates with itself over time. That's why it's called autocorrelation function and then autocorrelation window. Here, I give you an example from one of our recent studies. So here you see, so basically this is your time series, then you do a log, and that basically you get the frequency, here is the frequency, here is the frequency, here is the power, and then you get these curves. So this is an fMRI study here, this is 0.01 Hertz, 0.1 Hertz, so 100-second, 10-second cycle durations of your fluctuations. And you see these are different subjects. This is particular here in the cortical midline structure, default mode network. And you see the huge inter-individual differences. These are not artifacts. Yeah. And the measure, it's called the steepness of the curve. That's what is called the power law exponent. Here, I gave you an example of autocorrelation windows. So these are the time lags. So you correlate each time point with all other time points. And then, of course, you get lags. And then you see this is what is called the autocorrelation function. And then you get these beautiful curves. I always like them very much. And here you get a very small window. So here the degree of autocorrelation is rather short. Here the autocorrelation is very long. Yeah, this is typical for primary sensory regions, unimodal regions like visual cortex or auditory cortex. And this is typical for more transmodal regions, particularly with default mode network regions, cortical midline structures, ventromedial prefrontal cortex, displaying the longest autocorrelation window. So in these kind of things, you can measure. That's your signal dynamics. That's the dynamics. That's time, how time changes over time, the pattern in which time changes here in the frequency or in the time domain. And as I already said, I think I indicated that. And then you have a sort of what is called nestedness. I'm always a big fan of the Russian doles. Slow is very powerful, and the faster frequencies are sort of nested. So here's the largest Russian dole is really the slow frequency. It has the strongest power. The smallest one, here's a little baby, then is the faster frequency. And that's sort of a nested organization. That's very important. Yeah, and that's what you see in the brain too, in both temporal domain as well as, I didn't indicate that here, in the spatial domain. Yeah, smaller regions, smaller networks are nested within larger networks. Yeah, and what is important that the dynamic of timescales shows a certain intrinsic organization. I already indicated that in the cortical midline structures, the default mode region, what are often also subsumed as a core of the brain, you have the longest timescales. And then you have much shorter timescales here in blue. This is fMRI, this is EEG, in the sensory, in the posterior region. And what is important that you have a whole repertoire of timescales. Yeah? Because with your repertoire of timescales, your inner repertoire, your intrinsic repertoire of timescales, you approach the outer world and its various timescales. So sort of the shared feature, the common currency between your brain and the outside world, maybe the timescales. Yeah, and if your timescales match very well, your inner timescales of your brain match very well with the timescales of the outer world, as for instance in music, then you feel synchrony, you feel aligned, and that gives you a groove. Ask musicians, they know very well. Their timescales are tuned to the timescales of the music. Yeah. So you see that you have sort of a repertoire of timescales your brain can have, and yeah, and that's important for temporal integration, segregation, and putting different stimuli together, or not putting stimuli together, separating them. Yeah. So here I give you, for instance, another example of the intrinsic spatial organization of the brain, the topography. Here, this is a global brain activity, and you see the global brain activity is relatively strong here in primary sensory region and less strong in the default mode network region. And in task, it changes. But you see, it's somewhat also carried over from the resting state to the task. So the task is just a modulation of your resting state activity. It's really like the tip of the iceberg. Marcus Regler said is 5 to 10%. It's only metabolic change doing task-related activity, and 90% basically remains the same. That's your ongoing dynamic activity. And he's right in that. What we describe as task-related activity is just maximum 5 to 10% maximal incremental change in your ongoing brain activity. The remaining 90% is always there, even in the resting state. Yeah. So now you say, yes, Northoff, you showed me, you opt for non-specialness. Then you said, okay, that brought you to the brain's inner time and space. And then you showed me all these strange measures, autocorrelation windows, power law exponent, and there are others. There's sample entropy, Lempelsiff complexity, and so forth, you name it. There's a lot of, and again, all these measures you can get when you go into electrical engineering, signal processing, and physics. But you say, yeah, Northoff, this is all fine and dandy. I'm really interested in the mind. You haven't talked about the mind at all. You just said the mind is non-special, and then you came into this strange time and space stuff. Okay, so now I show you how you can link it, because that's exactly the idea, that we can measure these kind of measures, which I just showed you about topography and dynamic. Remember the global signal correlation, the global signal topography, and the dynamics, the power law exponent, and the autocorrelation window. Yeah, and I show you that these measures are very relevant for conscious state. So now I come back to neuroscience. I started in philosophy, then I went into neuroscience. I said, okay, I need to consider the brain's inner time and space. And now I said, okay, yeah, what on earth is the brain's inner time and space? Okay, then I ventured into physics and signal processing and engineering, and I got all these measures, power law, exponent, autocorrelation, blah, 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 you name it. And now I go back to neuroscience and say, okay, now I apply those measures to consciousness. So you see my iterative loop here, as I like to say it. You come from the specialness to the time-space, engineering, and now you can develop and acquire some data. And that's what I want to show you. Here, remember the scale-free activities, this power law exponent. How does it constitute consciousness? So here, I show you an example. This is a paper from Jianfeng Zhang, 2018 here. I just look at this. So this is anesthesia, awake versus anesthetic states. This is fMRI. And look just at this power spectrum, because I find this always very impressive. So look, this is a power spectrum in the awake. This is typical. As I said, this is 0.01, this is 0.1 hertz. And you see a lot of power in the slow frequency, not much power in the faster frequency. Now look at the power spectrum in the anesthetic state. It's flat. There's no structure anymore. So meaning your unconscious / non-conscious state in the anesthesia is no longer scale free. There is no structure in your power spectrum anymore. Yeah, there's no scale free dynamic. So the most basic structure of your power spectrum is disrupted in the unconscious state. Yeah, and we have further studies showing that. So this always finds these curves very impressive. And then if you say, remember, I had the example of the Russian dolls. So how is that related? We assume that that is related particular to the level state of consciousness. Yeah. So what you have usually, you have many different time scales when you're awake. Remember, I showed this example with the repertoire of timescales. You have seconds, minutes, hours, days, years, yeah, and meaning you have a high number of Russian dolls included. So, and that's what you see here. That's a typical power spectrum. Then, however, when you start losing consciousness, like in N1 or N2 sleep, or you become a little tired, your brain becomes a little slower. So your faster frequencies recede, the shorter time scales recede, and your longer time scales become much longer, the slower frequency. So you see this is indicated here. And this is, I know this is a schematic, but this is really data driven. Yeah. So suddenly your Russian dolls shapes are changed, the larger becomes much larger, the slower frequencies or the longer time scales become much more dominant compared to the smaller one. Yeah. And then when you completely lose consciousness and you cannot regain it, like in anesthesia, so there's no slope, no PLE anymore, there's no differentiation. And that's exactly the way I assume that how you perceive things. You don't perceive anything anymore because you don't have any temporal differentiation in your inner brain, time and space. And that's, you cannot correspond to the timescales of your environment. Yeah, so no differentiation between different timescales anymore. There's no difference between all the dolls anymore. So now the same thing is on the spatial side. So here we investigated again fMRI, different studies on different groups who lose consciousness, even red anesthesia, human sleep, and coma, unresponsive wakefulness state. And you could clearly see that your global brain activity, global signal activity, your global brain topography recedes and everything becomes the same. So you have a de-differentiation of your global activity. There's no difference anymore between the different regions. There's no difference anymore between the different timescales. Yeah. So meaning your most basic spatial differentiation and temporal differentiation is lost. Your repertoire becomes extreme, small, minimized, and ultimately zero. That's when you seem to completely lose consciousness. So this is indicated by this figure. So you have the global brain level, then you have the region and the networks, and then you have the local level. And of course, you could enlarge that. Yeah. And so you have a topographic differentiation from global activity to local regions. And here, this is basically, you have a larger dole and you have a smaller dole, and you have a huge number of dole in between. I think I read it up in Google. The highest number, the Guinness Book, the world record of doles is 51 included in the big one. Yeah. And then when you lose consciousness, you lose these Russian doles. You lose this spatial differentiation / the nestedness. Yeah. So that's basically here. Consciousness is about probably the differentiation and nesting of different scales. Yeah. It's a repertoire of time scales or space scales. Yeah. So it's a very basic fundamental feature of nature. It's nothing special. We don't need to invoke any special cognitive mechanism and so on and so on. Yeah. So here, since I stressed so much the example of Russian dolls, you have also on the Chinese side, the very refined craftsmanship. You can see here this in the crystal ball. These are all different crystal balls included in each other of different sizes. I think it's an unbelievable piece of craftsmanship. Yeah. So meaning your different scales in time and space, you need to have a vast repertoire. Why? Because with that repertoire, you have a better match correspondence with the abundance of time and space scales in your environment. So that's why we say consciousness is not inside the brain, but it really aligns and situates us through the time scales to the outside world. So we listened, our brain processes the different time scales of the environment relative to its own time scales, and then it puts things together. Yeah, and that in turn shapes your cognition. So that's why we say that the time scales are really key. The brain's intrinsic neural time scale and its topography are key for input processing. And I brought you many examples. Here's another one of the timescales. Now, this is an EEG, Federico Ciglio, postdoc of mine in Italy. So he measured the timescales, the autocorrelation window, in different states of consciousness. And he could observe, let's say here in sleep, you see a gradual prolongation of your timescale. So your timescales become longer and longer, and you lose your shorter timescales. And then, of course, your perception is no longer as precise. Yeah, because you lose the longer timescales, you use the shorter timescales, and then everything becomes integrated within the longer timescale. So you can see this, the parametric increase is almost, and we now want to use these kind of timescales for differential diagnostic of these states. Yeah, so it tells you the most basic and fundamental importance of this timescale for the brain. Here you see the same, you see this here in anesthesia. You can even see that the timescales, the autocorrelation window can distinguish between sevoflurane and ketamine anesthesia. So here you see here's the ketamine is much larger, much smaller change than in sevoflurane, much longer timescales. And what is even more important, it's shown down here. So here he included patients in a locked-in syndrome. So locked-in syndrome patients is a very sad state. They lose all their motor capacities. They cannot move anymore, show no action, but their consciousness is preserved. So they cannot speak because their muscle action doesn't work anymore. And their timescales are normal. Yeah, they're within the normal range. So they still have the whole repertoire of timescales. Yeah, so that's probably why they have consciousness. So here, this is a beautiful figure by Anne-Marie in our recent paper here in Trends in Cognitive Science. So what happens when your timescales become longer? So when you have sort of normal timescales, you can very well, so this action, this is a police guy, this is a thief. I always love this one here. So you see, and then the police stop right now, you never catch me, blah, blah, blah. So you need to, first you need to segregate all these terms. So to hear them each by itself. So you need short timescales. However, you also need to put this together. You need to put police, stop right now. So you need to put all that together. So this guy needs to put all those four together. So for that, he or she needs longer timescales. Yeah, like this one. Yeah. And here's the same of this one. So you need timescales for each word, but you also need timescales for the combination of the words, because that gives you the semantics, the understanding. Yeah. And then as an outside observer, you need an even longer timescale to see, this guy and what he says is related to this person and what she or he says. Yeah. So you need a long timescales to put them together. If you don't have them, these timescales, you don't perceive the relationship between those two guys. Yeah. So now when you lose consciousness, you lose the shorter timescales. That's what really your autocorrelation window becomes longer. So you lose the shorter timescale and suddenly it's more blurry. You cannot segregate these different words anymore. So you process them together. Temporal integration predominates over temporal segregation. And then it becomes blurry. And now when your timescales become even longer, meaning your shorter timescales disappear, you don't perceive much anymore. And at the end, when you just have the long timescales and no shorter, it's just one big blurry and black thing. That's the way I assume. Then you have only temporal integration and no temporal segregation anymore. That's the way I assume that these patients, these subjects perceive. So that is testable. Now you can test it even on the perceptual level, the temporal integration on the perceptual level. That's what we're currently doing. And this is based on data. Yeah, this is really data driven here. You see the long, extremely long autocorrelation function. So the basic idea that your timescale, and I mentioned that many times, that your intrinsic neural timescales are important because they match with the timescales of your environment. As a typical example, when you listen to a story, when you listen to my talk, I have long, short timescales included, the relationship between the different slides, within slides, yeah, and so on. Yeah, and you can pick all that up because your brain has timescales which match with the timescales I'm using, more or less, I hope. Yeah. And that's basically a stochastic matching. So it's a very basic temporal spatial dynamics. There's nothing special, no special cognitive process involved. Yeah, these are basic processes of nature. Yeah. And here, that's what we're working on, that you can really differentiate based on these time scales, your inner dynamic, your brain's dynamic, different conscious states indicated here. I don't want to go into detail, because that, of course, if that really works, if you can really differentiate these different states based on the time scale, we must do something wrong, something right. Sorry, that was a nice Freudian lapsus here. We must do something right. Yeah, and then you can also use this clinically, and that's ultimately what you want. Yeah. So what does it mean? I come towards now the end. What are the empirical philosophical implications? So what are, for instance, the theoretical implications for a theory of consciousness? So now I basically go back to my iterative loop here, my methodological transdisciplinary loop. Yeah, so now I say basically, what does it mean for a theory of consciousness? So I already indicated that the variety of different theories of consciousness, which we reviewed 2020, and based on our own this inner space-time dynamic, we developed what we call a temporal-spatial theory of consciousness. Was first published 2017. Now we just recently with Federico Cirio, we published an update on that. And the main idea is here, and this is obviously I cannot go into detail, really bridging the gaps between spontaneous and stimulus-related activity. How? Because we look at the topography and dynamic of the spontaneous activity of the resting state and how that shapes your stimulus activity. That's very important, because you have resting state theories like the entropy hypothesis of consciousness or the operational space-time by Fingerkurz. The first one is by Cartert-Harris. And you have task-evoked theories like the integrated information global neuronal workspace, etc. theory. But there's sort of a dualism of resting state and task-related theories of consciousness. Yeah. And then, of course, the second gap you want to bridge, and that is the key gap between neuronal and mental features, and that's the idea where time-space provides a common currency. So this is both a neuronal and, importantly, a neurophenomenal hypothesis. They're not the same. Yeah. Okay. So I don't want to go into detail. We proclaim the DTC proclaims 3 different temporal spatial mechanisms associated with 4 different dimensions of consciousness: temporal spatial nestedness, level state of consciousness. I showed some of that: temporal spatial alignment, the time scale, the matching stuff, time scale alignment. And then another mechanism, temporal spatial expansion, is the direct interaction of the pre-stimulus resting state activity with the external input, and then the globalization. But as I said, I don't want to go into detail about that. What is important here, that your time scales provide the background for your perception and cognition. Yeah, your single input is embedded within, which it probably operates in a very short time scale, is embedded within the longer time scales of your ongoing brain activity. This is what we discuss here. So you have a very short time scale here, input duration, but that is integrated within the ongoing longer time scales of your pre-stimulus stimulus activity. And that in turn is integrated with on your ongoing resting state. So you have a much longer time scale. Your input is about 2 seconds, but it's integrated within pre-post stimulus, let's say minus 2 seconds to plus 4 seconds. Yeah, that's from pre-stimulus to task activity. And then that in turn is integrated within the much longer time scale of your ongoing resting state activity, which, for instance, you measure during 5 minutes. So continuous integration and, remember, nestedness of the different time scale. And that's key, because the assumption is that here you have these 3 different time scales, which we indicate here. For instance, the IIT only uses very short time scales, 3 to 500 milliseconds, but that's the actual stimulus duration often. But those time scales are integrated within the longer, let's say, pre-stimulus activity time scales, and those in turn are integrated with the even longer time scales of your resting state activity. And then, so it's really converging that the temporal spatial theory sort of provides a larger scale, more comprehensive framework. Yeah, I come to the very back of my to the end of my talk. So then you say, yes, Northoff is all good. So you started with some strange philosophy, then you went to neuroscience, then you did a little excursion into dynamic system theory, physics, engineering. Then you went back to the neuroscience of consciousness. Then you postulated yet another theory of consciousness. Does that have any implications for philosophy? Yes. So this is an iterative suit. Does it also have back into that? Ultimately, when you really say, okay, the mind maybe is nothing special, then you should just say, maybe we need to really go back to the world itself and philosophy and explain how is the brain embedded and nested within the world. And the degree to which your brain is embedded and nested within the world, for instance, through the matching of different time scales, might then determine whether you have mental features or not. So suddenly what you declared as a world mind-body problem then becomes a problem of how the brain is integrated within the world and what I would call world-brain relation or world-brain problem. Yeah. So suddenly you have a shift in your philosophical problem. So with this sort of iterative methodological loop, you get even something out. So you get a new view on the brain mind, you get something out for neuroscience, a new approach, and you also get out a new approach, a new problem on the more ontological or epistemological level, shift from mind-body to world-brain problem. As I said, this is more philosophical territory. So this is really an iterative methodological loop, and I can only encourage such a interdisciplinary or trans or cross-disciplinary, whatever you want to say, continuous iterative movement. And it's very interesting and highly rewarding. And even if you say, I'm not interested in philosophy, but at least listen a little bit, and because it has an impact on the kind of concepts you use as a starting point for your experimental investigation. And that in turn impacts what exactly you measure and how you measure time series. Yeah, that's very important. So, and when you go into the science, let's say physics and also biology, they're always strong conceptual presupposition. Darwin shifted them, Einstein shifted them to a huge degree, and that impacted their empirical data or the mathematical formalization. And with that, I go back. So we really have, I hope I showed you the need for philosophy or the need for a truly cross-disciplinary approach. Thank you very much.